Today we're going to start with an introduction to integrals and Riemann sums. Please make sure you have your notes out so that when we go through them, you can follow along. What exactly is an integral? Well, I want you to always remember that whenever I ask you what an integral is, that it's an area under a curve. When we do an actual calculation, we're going to be doing a reverse or backwards operation of a derivative. Basically, an integral will get you the stuff or the quantity that you're asked for when I give you the rate of change. You're undoing a derivative. It's also the limit of a sum, and that's kind of what we're going to work on for the first few days before we get to the middle bullet. Today, we're going to do the first bullet. So like I have here, we will explore all of these ways during this section. Let's first talk about general area. So here are some equations you need to know. Please make sure you write these down. You'll definitely need to know the area of a square. It's just sides squared. You'll also need to know the area of a rectangle, length times width, area of a trapezoid. It's a hard one, but you need to have it memorized. 1/2 the first base plus the second base times the height. Area of a circle you should know by now is pi r squared. And area of a triangle, 1/2 the base times the height. Now, if you have these shapes down here, like this hexagon or this weird thing that kind of looks like a SD card or this little house or this thing, basically, you need to know how you would find these areas. So if it were me, I might divide this into a trapezoid on the top and a trapezoid on the bottom. You could divide it into two triangles with a rectangle in the middle. You could divide it all into a bunch of triangles. The point is, you can divide this hexagon into these shapes and use these formulas to get its area. This one's a little bit different. You would have to take the whole rectangle and take out this little notch, which is a triangle. You could also draw a line this way, vertically, and make this into a trapezoid and another rectangle. This one, this house-looking one, you could divide right down the middle if you want. You could go ahead and do across the top. So down the middle would be two trapezoids. Across the top here would give you a triangle with a rectangle. And then this one over here, I think the only option is to draw a vertical and do a rectangle and a half a circle. But again, all of these shapes we can find the area of by using formulas you already know. Well, now what about something like this? I want the area of the region labeled S. This is the area from this curve f of x to the x-axis from the variable a to the variable b, and I shaded it for you. What formula could you use to find the area here? Looking at it, it looks like I can maybe draw a horizontal and then do the rectangle on the bottom, and then a triangle on the top and a triangle in the corner. But is it going to be exactly a triangle over here? Is it going to be exactly a triangle over here? Will you get all of the area? Now, what do you think happens when you move the area below the x-axis? The x-axis is going to be very important in this section. Well, I want the area from this curve to the x-axis, from this value a to this value b. It's kind of shaded here. It doesn't look as shaded in your notes, but it's kind of shaded here. Well, now that it's below the axes, again, I can still try to break it up into formulas I already know, but it might not be exact. The thing I want you to worry about here is that this area is below the x-axis. That's kind of strange. In calculus, we usually can't have negative values for quantities like area, but now you can. Whenever you have area below the x-axis, that means you will have a negative area. Yes, area can be negative in this section. It's just something you'll have to get used to. Now, also in this section, we are going to calculate areas between curves in the x-axis, and the thing they call that in a book is the area under a curve. So it might not necessarily be what looks like an under, but it's the area between the curve that you're given and the x-axis. Here's some examples. From this curve f to the x-axis, from a to b, it's above the axes, it'll be some positive area. Now this curve f to the x-axis, it's below the x-axis, so I shaded the area I'm describing, and that one below the axis will be negative. This one, here's the curve f of x, and I want from a to b, it crosses the axes at c. So I want the area from the curve to the x-axis. this piece would be above. And then from the curve to the x-axis, I have to travel up, but it's this area right here. It's not under here. Look at where the arrow is. It's not under there. Here's a parabola. This parabola is above the axes, below the axes, above the axes. Positive area, negative area, positive area. That is not a coincidence. That is the same as above, below, above. Remember that when you're talking about where the graph is located and the area you're looking to calculate. So we can also estimate areas of these strange shapes with formulas we already know, but the most common way is to break up the shape into rectangles. All rectangles. No matter what shape you're given, I want all rectangles. So for this section, if you can find the area of a rectangle, then you can estimate the area under the curve of any function I give you. Adding up rectangles to estimate an area is called finding a Riemann sum. Whenever you see the word Riemann, you need to think rectangle. Now we can draw our rectangles in a whole bunch of different ways. The ways that you're going to see are inscribed, circumscribed, or a little bit of both. So look at this first section here, this first example. Here's my curve. My area is from A to B. It's this stuff where all the rectangles are. These rectangles are underneath the actual curve, and I'm going to use that to estimate the area. Well, if I do that and it's underneath, it's called inscribed. If I draw my rectangles so that they go above or on the outside of the given area, so the area is underneath this curve, and then these little triangle pieces are on the outside, that's called circumscribed. Now, you can kind of try to get a better estimate by doing a little bit of both, but that happens where you have to maybe do a midpoint or something else, and we'll get into this a little bit of both stuff later. Now, look at these. Are they overestimates, underestimates? Is there any connection to the fact that these functions might be increasing? They're all concave up. What if they're decreasing and concave down? We're going to look at that on the next slide. I think you can see that this is an underestimate, this is an overestimate, and then this one looks like my best estimate. It's really all going to depend on the problem. If you look at the next page, I have 4 pictures of concave up, concave down with increasing and decreasing in each. I want to first show you what inscribed rectangles look like. So in this scenario, concave up and decreasing, here is what inscribed would look like. It would end up being underneath. The same thing in this one, and this one. They're all underneath the curve. But again, how does that look in the picture? Well, you're going to have to go down this way, up this way, and then circumscribed for all 4. You can see I drew above each of those curves. Now, today in the examples, all the rectangles are going to have the same sized base. So I'm going to use these rectangles and add them all up to find the area under the curves that I give you. But the fact that the rectangles all have the same base, that doesn't always have to be the case. You can calculate Riemann sums in a bunch of different ways. We're going to determine our heights using left endpoints, right endpoints, and midpoints. How do you know which point to use? That'll be told in the type of Riemann sum you have. For example, you're going to see down here in the example we'll do in class when I see you next, that left endpoints, right endpoints, and midpoints, this is how you're going to determine the height of a rectangle. Every time you do a Riemann sum, for each rectangle you're talking about, you're going to need to find the base and the height of that individual rectangle. To find the base of the rectangles, in these particular cases, you're going to need to calculate the length of the subinterval from the beginning of the rectangle to the end of the rectangle. To find the height of the rectangle, you will need to find the y value at the specified x value that you're given. So by that I mean the specified x would be the left endpoint is your x, the right endpoint of the rectangle is your x. So what you're going to do when we come to class next is I'm going to go ahead and find the Riemann sum that estimates the area under the curve of this parabola between 0 and 4 using 4 subdivisions. I'm going to draw this picture. I'm going to draw a vertical line at 0, a vertical line at 2. and I'm going to chop up the area under the curve into 4 rectangles. So I'm going to make them all of an equal distance apart. So if I have the distance from 0 to 2 divided into 4 rectangles, the base of all my rectangles is going to be a length of 1/2. Then I will from there take those x values, a new x value every half a unit, and label them left, right, and then later calculate the midpoints of each rectangle. Once I have all of that, I can take all those x values, plug them back into this function to get the y values, which will give me my heights. So remember, whenever you are finding a Riemann sum, you need to calculate the area of rectangles. Your job is to figure out the dimensions of each rectangle. So when you come to class next, please make sure you have all these notes and any questions that you have ready to go, and we'll start with this example.